Good morning, mathematicians. What are we going to yap about today? Gosh, I don't even know. I have some ideas. Maybe representation theory stuff. You know, that's the huge. There's one thing I kind of want to take a look at, actually. It's yapping time. You got it, Locke. Time to yap. Yeah, time to yap. There's a book, since someone was talking about the orbit method yesterday, it got me thinking about this book that was mentioned in this orbit method reading group seminar thing that I've been in. Where is it? This is the book. Front matter. Let's take a look. Induced representations of locally compact groups. That's what it's called. Yeah, so this is all about I don't know. Do I want to commit to another reading series? Like, should I go back to Galois cohomology or spectral sequences? Hello, Matthias. I was looking at stuff on spectral sequences this morning. I was trying to think, what should we go to? I don't know. Actually, there is this one. You know what I should be doing is trying to understand this one paper that I mentioned before, that I brought up before. This is what I should be doing. I should be looking at this paper. So why don't we start here? We need to understand operads. So maybe we should go back to reading about operads. Yeah, I mean, isn't that just the mathematician's way? Starting new stuff when other stuff is unfinished? Yeah, we'd started reading a bit about operads from that thesis. But, okay. Like, I know there's something called the Lie operad, so maybe if we dive in with this example. Notes on the Lie operad, yeah. I mean, let's check NLab first. Given an ambient, additive, symmetric monoidal category, the Lie operad is the operad whose algebras over an operad are Lie algebras in that category. That's quadratic operad. So here's another interesting thing. Koszul duality comes up in my research area, and I know that there's a version of Koszul duality for operads. Whose Koszul dual is the operad for commutative algebras. Very interesting. Is this the one we're about to look at? Trimble? Yes, it is. Okay. The purpose of these notes is to compare two distinct approaches to the Lie operad. The first approach closely follows the work of Joyal, which gives a species-theoretic account of the relationship and homology of partition lattices. Second is rooted in a paper of Ginsberg and Pranav, which generalizes within the framework of operads a fundamental duality between commutative algebras and Lie algebras, as we just saw. Both involve a bar resolution, but in different ways. We explain the sense in which Joyal's approach involves a right resolution, whereas the other one is left. Okay. What strange notation. Hello, Arad. FB is the category of finite sets and bijection. Okay, actually, I guess that makes sense. Equivalent to the permutation category. I'm not familiar with that notation, but the fact that it's equivalent kind of tells me everything I need to know. You don't understand the last two sentences of this proof. Of what proof? Could I elaborate and then explain to you? Well, I don't know the statement. You'll send me a picture. You probably won't be able to read. Okay. Possibly. Possibly. Operads and tetrads. I think if you mean like the tetrad operation, I think they're very different things. Oh, it explains it here. The permutation category whose objects are natural numbers and whose set of morphisms is the disjoint union of all finite symmetric groups. Wait, what? Okay. Wait, what? Whose set of morphisms is the disjoint union? It seems strange. Okay, let me see. Let this denote the elements in ZP of order E. Then we have the number of elements is at most Euler's phi function of E. Okay. And your issue is with the very last line of the proof? Right. B times E over the GCD of M and E is equal to 1. Okay. Let's see. E is the order of B. We therefore have that these represent all the roots of the polynomial. Okay. So why is this true? Right. Well, because you have this divisor. Sorry, I lost you, chat. Basically, you have. B. You're the sleepy DP guy today. Me too. I woke up at like 5:11, and it's like 7:47 now. I don't know why. It was kind of hot in my room. Maybe that's why. I don't know. Right, but the GCD of M and E divides M, so M over this is some integer, call it D. So that whole expression times E is just B dE, which is BE to the power of D, which is 1 to the D, which is 1. You said last two sentences of this proof. So let's see. That's why it's equal to 1. So B to the M cannot have order E. Wait, why can't it have order E? I mean, E is supposed to be the smallest number that you put it to the power of to get 1. Right. So definitely if you put BM to the E, you get 1. So its order is at most E. But also, right. But then also, this tells you that B to the M to the power of E over the GCD of M and E is equal to 1, right? So if GCD ME is greater than 1, then the order of B to the M would be less than E. Sadly, gonna have to dip early today. Well, hey, if you want to catch up on what you missed, the recordings are always online. Hello, Kostaka Corey. Also had too much fun making Pure Math Jeopardy questions. Hell yeah, I'm looking forward to it. Chat people, let me know if you want to be on Pure Math Jeopardy. Yeah. Pure Math Jeopardy. I thought you already knew Arad. I thought you were already in on Pure Math Jeopardy. That's what Leo told me. Gonna run a Jeopardy like YouTube live stream. Yeah. So pay attention. Stay tuned for that, gang. Can I please suggest some video lectures where you can learn measure theory? Oh, that's a good question. I actually don't know about any video lectures on measure theory. Yeah, that's a good question. This proof would be much easier if they just used the ETH cyclotomic polynomial. Isn't that what they do earlier on in this proof? Yeah, that's exactly what they're doing. Right? That's exactly what they're doing. They're using that B up to Bn represent all the roots of the ETH cyclotomic polynomial. That's exactly the approach. Right, so Bm cannot have order E unless this is true. Therefore, at most, this many of them have, right? And so that's why we get the second sentence, right? So we just saw the only way that B to the M would have order E is if GCD is equal to 1. So that's a restricting condition. So if B to the M had order E, then it would be the case that GCD M and E have GCD of M and E are equal to 1. And that's the proof. That's it. The representation theory textbook I've signed you up is quite interesting. Wait, which one? Which one did I tell you to look at? It goes into Fourier analysis on groups. Yeah. Instead of hardcore module theory stuff. I forget which book I told you. But yeah. Yeah. No one got your what is joke? Does sound funny though. Wait, what? Oh. Very clever, Rod. Yeah, that was good. Totally missed it. There may or may not be measure theory question or 2 in the Pure Math Jeopardy questions. Uh-oh. Oh, Steinberg. Oh, okay, nice. Great. I'm glad you're enjoying Steinberg. Yeah. Yeah, the Fourier analysis stuff is important. Okay, where were we? We were reading about operads over here. Anyways, this satisfies a universal property given a symmetric monoidal category and an object A of C. There exists a symmetric monoidal functor which sends the one object of P to A, and this functor is unique up to unique monoidal isomorphism. Okie dokie. If V is a symmetric monoidal closed category with monoidal product. Wow, that's a weird monoidal product. In unit 1. Oh, let V be this. For the time we assume this is complete and co-complete. Okay. Okay, let me write down some definitions. Well, I definitely can't help you with hypothesis testing questions. Not even remotely. I wouldn't even begin to try. God, I wish I could make some of these extra bars disappear and stuff. Okay. So, V is symmetric, monoidal, and closed with monoidal product this and unit 1. And we'll say it's complete and co-complete. So a V species, I've never heard this term in my life. V species is a functor from finite sets with bijections into V. And the category of V species with natural transformations is this. Okie doke. Gonna go now. Have a nice operadding. You too, Locke. Also was coming up with a lot of fun true-false questions, but realized that is silly for Jeopardy. Yeah, maybe not. Yeah, because you got to say what is. What is true? And you got to have Boolean logic questions. What is true? So they're all now which of these are true questions with 3 to 5 statements. That's still not really the Jeopardy theme, though. You're not familiar with species, but surely the functor should be monoidal. Maybe. I mean, it says that this category carries several monoidal structures, so I don't know. This YouTube channel has become your NLab. Sweet. Another topic you have no idea about. Cool. One is the day convolution induced by the monoidal product on FB. Okay, so shouldn't that mean that we're asking that it be monoidal? You might be right. What is 2, 4, and 5? To set this up, we work in the context of a V-enriched category theory. And recall, any locally small category can be regarded as a V category. Okay. By composing Hom with the symmetric monoidal functor, sending a set U to its index product. Whoa. What? And then the day convolution is given by this? What? What is F and what is G? Is there a notation missing here? Were you supposed to notate some of these functors? What is going on? Okay. What is going on in this introduction? Where am I? I'm skipping past this. Operads. An operad in V is a monoid in the monoidal category, blah. Oh, I guess we do need to know about the substitution product. Uh, why does this seem like, I don't know? Is it just this complicated? I feel like it's too early. I don't want to. I don't want to read these details. Uh, okay. A special case of this. Okay, I guess we got to read some of this. Universal property may be exploited to yield a second monoidal structure. Let this be the category of co-continuous symmetric monoidal functors. Then universal property may be better expressed as saying that the functor that evaluates a species at 1 is an equivalence. In this case, the monoidal structure transports across the equivalence to yield a monoidal product on here. But we have an explicit formula anyways. Still not sure what G is supposed to be in this case. And you specifically went to algebra to avoid integrals, yeah. They'll find you. You can run, but you can't hide. Yeah, I mean, isn't all of math just fact recall? I just recall the proofs of things and then I'm done. What was I going back? Yeah, we don't know what our G is, right? We weren't told what G is. Whatever. I could probably sauce it out from context. Okay. So here's their definition of an operad. It's a monoid in the monoidal category here. The tensor algebra done by this. Okay, what's the other? A look ahead. In the next few sections, we'll reprise the beautiful work of Joyal. Yeah, where's the Ginsburg version? Whoa, we have a PBW type theorem. That's pretty cool. Okay, these species. I mean, this is maybe interesting, but I don't know if this is what I don't know if this is relevant to what I need to understand. Let me go back to this paper. Shouts out to the papers you've been reading lately that have been doing information theory, mixing integral sum signs, where they're all discrete sums. Colimits are friendlier than calc limits? You're very algebra pilled. You are very algebra pilled indeed. I guess we could just look at the definition here, right? An operad in C is a symmetric sequence, which is a monoid with respect to the product. Wait, and we're assuming a monoidal category. An operad is designed to encode a system of algebraic objects. In our category, we have an object which is either a DG module or a space of n-array operations for each n. In top, symmetric space. A symmetric sequence would simply be a sequence of spaces equipped with an action. An operad is a symmetric sequence, which is a monoid with respect to... So I guess we're assuming that we have some monoidal category. Yeah. Okay. But let me get a sense of what I need to know. The operad algebras... What do I need? Operad algebras. Spectral sequences. And there's some serious topology that comes up. Okay, but I do need to just learn the operads. I don't know. Let's find another source here. Maybe a hot take, but you think the introduction to the section on operads in higher algebra is not so bad to learn from? Well, let's take a look. $1,500 pages. Jesus Christ. This is going to take 3 years to load. I guess maybe I should download it. I wonder, I probably have a copy somewhere buried in my hard drive. Infinity operads. Is there a normal operad somewhere? Does he talk about normal operads at the beginning of this? Because I don't think... Oh, this does look like maybe there's normal operads for a moment here. Okay. Commutative monoid, symmetric monoidal category. We begin by considering example bilinear maps. Rather than a bifunctor. Oh, okay. Okay. Let's read some of this. That's like 50 times spectral sequence stream series. What, the number of pages? C is a category of complex vector spaces with monoidal structure given by tensor product. Given a pair of spaces, the tensor product is characterized by the requirement that can be identified with the set of bilinear maps. In fact, this property really only determines this up to canonical isomorphism. In order to build an actual tensor product functor, we need to choose some particular construction. Because this requires making decisions in an ad hoc manner, it is unrealistic to expect any quality of vector spaces. However, the existence of a canonical isomorphism is easily explained but by trilinear maps. So this example suggests we might reformulate the definition of a symmetric monoidal category as follows. Right, we specify for each n tuple and each d a collection of morphisms The relevant data can be encoded in a new category. Okay. SAG is sitting at 2,300 pages. Wait, SAG? What's SAG? Spectral algebraic geometry? Let me download this book. I'll probably want to refer to it again. Where's my download button? What? Oh, here we go. Sure, put it on our desktop. Higher algebra. Lurie. How much do you hate your contestants? Yeah, a lot, Arad, because apparently it's you and me. So it's a good source of many straight facts, terms, questions asked. Like you could give a property of morphism and ask what it's called. Oh, I'd be cooked. I don't remember anything. So a monoidal category is anything that admits a bifunctor together with some identity element object under tensor products. What about other products? Well, well, it depends what you mean by tensor products. Like the point is like you can use like monoidal categories to define what like a tensor product is. Like the point, I guess, of like a symmetric monoidal category is that it's kind of like a big generalization of tensor products, of your category having tensor products, as opposed to having products or co-products. But I mean, it can happen that your product or co-product ends up being, I think, like the monoidal operation. Yeah. Oh, you were thinking of SGA, spectral geometric algebra. Yeah. Yeah. Exclusively for Cartesian products of sets? That is disgusting. I guess it makes sense, but I don't know. Okay, so an object is a finite, an object of this category is a finite, possibly empty sequence of objects from some other category. A morphism consists of a subset, a map of finite sets, and a collection of morphisms. And a collection of morphisms in the category. Here, tensor product, the product is well defined up to canonical isomorphism. Since C is symmetric monoidal. Okay, hang on a second. What are we trying to define here? I thought we were trying to define symmetric monoidal. So why are we using symmetric monoidal? I thought this was clear. Oh, hi, Mom. Love you. Hope you're doing well. That thesis has several crimes of notation. Well, good to know. Symmetric monoidal category. Oh, sorry. Okay, so we are assuming it's a symmetric monoidal category, and we're defining this new category. And I guess it should be equivalent, and then that's going to inspire the new definition. Okay. And then suppose we were given morphisms here and here. Okay. To analyze this construction, we begin by recalling Siegel's category of pointed finite sets. How is this going to help us? For every symmetric monoidal category, the category from this construction comes equipped with a forgetful functor that carries an object to the pointed finite set N. Okay. What is going on here? Where is the definition of operad? Arad, how is this better? Come on. You're also adding in a challenge system. If you think you're right about a Jeopardy question and I am wrong, I can prove it in a few minutes. and can prove in a few minutes, you get double points. But the loss potential is huge. Interesting. Okay, here's the definition of symmetric monoidal infinity category. From colored operads to infinity operads. Okay, where's that? Where's that section? Oh my god, where is it? From colored operads to infinity operads. Oh, here we go. 171. Okay. Why do category books like to construct new categories out of other categories? When does it stop? Well, why do we do anything at all? Why construct real numbers out of complex numbers? And then real numbers out of rational numbers. And then next the complex numbers. Where is it going to stop? What, are we going to invent finite fields next? What about building sets out of other sets? When is that going to stop? Have mathematicians gone too far? That's my counterpoint to you, Dason. But why is this colored? I just want to know the operads that I need to know for what I need to do. I guess colored operads are what, easier maybe? If Lurie constructs more categories, we will all construct more categories. It'll be anarchy. This is all beyond you. Well, it's a little beyond me. Grothendieck universes are too far. Oh my god, Leo. Every day you show up here and you're asking me to revoke your blue gear. You beg me to remove your blue gear icon. Okay, a colored operad consists of a collection. I always don't love this notation. If you don't want something to be strictly countable, maybe your take was too hot. The world isn't ready for it. Could be. We'll indicate that X is an object. For every finite set, every I-indexed collection of objects in O, and every object Y in O, a set multi, right? Which we call the morphisms. Right, and this is just our composition law. I remember vaguely when we were reading about operads before. We just wanted to, right, we had something like this, and we wanted to make sure that we had good composition laws. For our operad, so maybe you're too hot. Well, let's go warn the world to prepare themselves just in case it's true, Leo. Set of morphisms. What you call the set of morphisms? And we have some composability condition. A collection of morphisms which are both left and right units. Okay. What makes this operad a colored operad? How is this different? How is this different than other definitions of operad I've seen? Hello, Dylan Hafner. It's just repeating the same thing over again. Next, it's going to define some generalized product of this new multilinear map. Will it? I don't know. Every colored operad has an underlying category, right? Just by ordinary maps from the one-ary maps. So we can view it as a category with extra structure. Simplicial colored operad. Oh, here we go. An operad is a colored operad having only a single color. Okay. Wait, does that mean we have a single object? I see. Okay. Classical operads are like colored objects. Oh, and then Arad happens to say that at the same time. Nice. Okay. I see. Right. And I do actually recall this from definitions we've seen before. So we sometimes refer to this as a set of n-ary operations. The structure of O as a colored operad, right, is determined by those sets, together with actions on the symmetric group. Okay, why is that? Why is that the case? So, hang on. What is N here? The structure of O as a colored symmetric operad, together with actions on ON and the substitution maps. Because the definition asymmetrical. Wait, what's going on in the substitution map here? And it's not clear why do we have an action of the symmetric group? Democrat operads. Yeah, what is the cement? Why do you? We're just calling any of these maps substitution maps. Okay. Oh, I mean, maybe substitution maps was defined earlier for colored operads. Maybe. The substitution is the tree that I just drew. That's it? Okay. And symmetric group makes all the operations commutative. It's not always assumed. Oh, I see. Wait, so then are we assuming commutativity here? Not every operad. Wait, what does commutativity even mean? What does commutativity even mean here? Do we always want this to be symmetric? It follows from this analysis we can regard the notion of a symmetric monoidal category as a special case. Do I have a paper nearby, or are I complete MS Paint maniac? I no. I mean, I write in OneNote, in my for office hours. I write in OneNote, and I use OneNote in all of my other videos. I do use Paint for my thumbnails. I do use MS Paint for my thumbnails. Like if you have any n-area operation, you want to be able to turn it into a new operation by just permuting the inputs. I agree. I agree. I'm still a little confused, but okay, whatever. Maybe you want to, Rad. Yeah, but what about the rest of us? Okay, I think it's time to end the stream soon. But okay, the operad learning. Ooh, you beat Leo to it. Leo was about to call you a symmetric operad with a frowny face. Got him. I guess I was just thrown off by this tensor product. But we could just call it whatever, right? What did you stumble on? Brimming curiosity? Well, I mean, being a curious person, it's unsurprising that you'd stumble upon all the weirdest, wackiest things on the internet. I'm reading something about spectral sequences and operad algebras. Yeah, that's what it is. And we were just reading a little bit of Lurie's higher algebra. But I think you've come at the end of stream, so you'll have to join us again tomorrow, where we continue the adventures in learning about operads. Okay, so that's gonna do it. Thanks everyone for why do I say I've said that in several videos. That's gonna do it. That's not a complete sentence, like that'll do it for now. Oh well, that's my new catchphrase. That's gonna do it. It's intentional. You have to turn on notifications. Yes, that's true. Yeah, click the bell and subscribe. I hate that. I've never said that in any of my videos. I don't know why. I guess I'm too proud. I guess I feel like, I don't know. It's almost like, I mean, some people say it really makes a difference in how many people subscribe to your channel. But also I'm like, I don't know. You guys are smart. You can figure it out. You can subscribe. But maybe there's some psychology thing that if I tell you to, you do it. I don't know. Subscribe. Turn on notifications. Okay. Anyways, I'm peacing out. Yeah. QED.